Good evening, everyone, and welcome to the Datathon workshop series. I'm Chamudi Mallavarachi, Ambassador of WIT Sri Lanka, your host for today's workshop. We are thrilled to have you here as we embark on the final day of this exciting journey of learning and discovery. Our workshop series promises to be a valuable learning experience, and we have some fantastic guest speakers lined up today to share their insight. I kindly request all the participants to rename yourself with your first name and last name. Before we dive into today's workshop, let me give you a brief overview of what WIT is. It is an organization with the aim to empower women to reach their full potential in the field of data science. We elevate and celebrate the outstanding of work of women on a global scale. Collaboration, connection, and the inspire education and support, so that vibrant voices and ideas can be shared with the world. Let me give you a brief introduction of the WITS Global Datathon Challenge. Gilead Sciences is the sponsor of this year WITS Datathon. This challenge theme for Datathon 2024 is Equality in Healthcare. We are thrilled to hear announce that is 7th annual WITS Datathon competition. Participants are tasked to developing a model to predict if the time for patient to receive their first treatment for the diagnosis in within 19 days of their metastatic cancer diagnosis. Datathon is designed to help you discover whether disparate treatments exist and understand the drivers of those biases, such as demographic and societal factors. The primary goal of building this model is to detect relationship between demographic of the patient with the likelihood of getting timely treatment. The first challenge of health inequity it has become a global challenge. Addressing the challenge has extensive positive impact on women's health, which is the key societies of economy to do. We have provided a rich worldwide dataset which contains treatment and insurance provided about patient to we are diagnosed with the breast cancer from 2050 to 2080. I welcome you all to be a part of the Worldwide Challenge Datathon 2024. Without further ado, let me introduce today's distinguished guest speakers as we have two speaker sessions today. First session will be conducted by Ms. Malshini Nissanka, Data Engineer at North Technology Group, and second session will be conducted by Ms. Ushani Amarasekara, Executive Data Analysis at Mass Krida. They are expert in the field of data science. We are honored to have Ms. Malshini and Ms. Ushani here with us today, share their knowledge and insight on data science and machine learning. Ms. Malshini, the virtual floor is yours to conduct the first session for today's workshop. Please enlighten us with your wisdom and expertise.
Good evening, everyone, and thank you, Chamudi, for that introduction. Hi, everyone. I'm Malshini. As Chamudi mentioned, I'm working as a data engineer for North Technology Group at the moment, and I'm delighted to conduct this session for you, which is the final session of this Datathon workshop series at the hands-on session. So today, I'll be doing the first part, which is the data pre-processing part. And the Ms. Ushani will be followed with the model training part. So without a further ado, let's get started. Let me share my screen. Can someone confirm if you all can see the screen?
Yes, we can see.
Thanks. So since this is a hands-on session, I would expect this to be more interactive. And I hope today's participants are ready with a collab notebook and the dataset. Is there anyone who doesn't have the dataset that we'll be using today, which is the Indian diabetes patient dataset? If so, let me drop the link into the chat. Is there anyone who is not familiar with Collab's notebooks? If so, you can raise your hand. Okay, cool. Seems like everyone is familiar with Collab notebooks. Yeah, so let's get started with the data pre-processing part. First, I have imported some libraries. Here, we'll be using the Python language throughout the session. So I have used this pandas. I'm using it since I'm using pandas data frames, and NumPy for some calculation, and Matplotlib and Seaborn libraries are for data visualization. And apart from that, I'm using this standard scalar and label encoder, which I'll explain in the latter part. So first, we can load the data set into a pandas data frame using this command. So you can pretty much use the same command. You just have to change the path to the CSV file accordingly. So we can do first we can do a simple display of the data set just to have a glance at it. So the objective of this data set is using these medical measurements to predict if a patient is having diabetes or not. So that's the goal of this data set. And feel free to ask any question in the middle. You can drop into the chat or unmute yourself and ask it. So today I'll be starting with exploratory data analysis, which will help us to understand this data set in detail. If there's any issues with the data set, like missing values or anomalies, or even like if to identify the patterns, relationship between variables, and so on. So we'll be starting with an EDA. I hope you have covered the exploratory data analysis in deep in previous sessions. So there are mainly 4 categories. Univariate analysis, where we'll be analyzing each variable separately, and multivariate analysis will be like analyzing multiple variables together. And further, we can divide them as graphical and non-graphical. So I have started, I'll start with like simply displaying the information about the data frame using info function. Yeah, so here we can see this dataset has 768 entries and total 9 columns. So these are the columns. And here first 8 columns shows the predictor variables, measurements, medical measurements. And the last variable is the outcome, which is the target value. That means whether this particular patient has diabetes or not. And then also we have the non-null count. So according to this data, it seems like this dataset doesn't have null values. What does that mean is this dataset doesn't have any empty values. But when we go further into the dataset, we might find there are some null values, incorrect values. Just because here it says the non-null count is 768, which means there's no null values, doesn't mean that this data set is complete. And finally, we have the data type as well. As you can see, all the variables are numerical, integers or floating. There's no object variables, categorical variables. Yeah, now let's get the statistical summary of the numerical data using this describe function. So using this describe function, you can get these basic statistical values like count, mean, standard deviation, and min, max, and different percentile values as well. For example, if we take age, it gives the number of record counts, and the mean, which is 33 years, and min value is 21 years, and maximum age is 81 years, which makes sense in practical scenarios. So using this DF describe, you can get the statistical summaries for numerical features. And even though this data set doesn't have any object variables, that means categorical variables, this outcome variable is supposed to be more like a Boolean variable where it's 0 or 1. And to show you that how to get like a basic summary for object variables, I have converted this outcome variable to object type, and using include O inside this describe function, we can get the summary for object variables. So this is how the summary comes for object variables. First, it shows the count again, similar to the numerical variables. Then it shows the number of unique values. So in the outcome, we have only 0 and 1, so it's 2. And then top gives the most common value. So in this data set, 0 implies no diabetes, 1 implies diabetes. So majority of the patients don't have diabetes. And the frequency is the frequency of top category. That means there are 500 patients without no diabetes. So yeah, I just converted this to object, so you can get the object variable summary as well. So these are non-graphical. Then let's move to the graphical analysis, which will give more insight at a glance. Like if you see this, we might have to go one by one and like kind of create an image in our mind. But with the graphical ones, we can grab more information, insight at a glance. When it comes to the graphical analysis, there are like ample number of visualizations available that we can use for different type of analysis. I'm pretty sure you have covered them in the previous session. So in this particular exploratory data analysis, I will be using the box plot mainly. So let's first plot the box plots for each variable separately. Yeah, so here, as you can see, like at a glance, you can see the distribution of these data set variables, as well as you can grab some of the statistical outliers in these variables, indicating from these circles. Yeah, so if we look into one of these box plots, let's take the age one. Here, it shows like there are more patients lying in the more towards young to adult, mid-adult category. And it also shows some outliers. So from like about 65 to 80 years old patients, this particular box plot has indicated as outliers. So here, one thing you have to consider is what these plots and all these statistical summaries or numerical summaries use is the values based on this data set and those and statistical summaries. In this case, even though this here it shows as the outliers. If we take the real world scenario in practical, it's possible. There are a lot of patients in this category, right? It's not uncommon or it's not impractical to patients in real world who are age 60 to 80 years old. So always when we are doing the exploratory data analysis, it's required, it's important to always have the knowledge about the problem you are going to solve and the knowledge about the domain related to that problem. Rather than like just slowly depending on these visuals and the values, it's always important to incorporate this external knowledge you are having to analyze and derive insights from these. So in this case, it might not need to treat these patients as outliers, because this is quite common scenario in the practical world, and having these will help to more generalize our model as well, to generalize the data set as well. And apart from that, if you can see these, we are having some in glucose, blood pressure, and this BMI plots, we are having bit darker, thicker circles in the x-axis. That means in this x-axis at the value 0, we are having many outliers. If you can remember, when we first checked the information about dataset, it mentioned that there are no missing values. There are no null values. But here, if we incorporate our general knowledge, it's impossible to have a glucose level of 0, blood pressure of 0 units, which means these 0 values implies the missing values. That meaning this data set or missing values has been replaced by zeros. So we need to address these missing values either through imputation with some statistical measurements like mean or median, or else if the missing count is high, we can decide to drop that feature as well. Yeah, so those are few of the insights we can get through these box plots. Also here in the pregnancies, if we can see there are some outliers in the upper boundary. We can either consider them as outliers or not, because having like 17 pregnancies, it can happen. It's not something impossible, but it's highly unlikely. So in that case, to avoid the overfitting of the model, we might consider to like remove those outlier through a proper way. Is there any questions so far? Seems like no. Let's move on. Yeah, so these box plots are pretty much univariate. So we can further to get the further details, further insights. But next, we can plot these visuals based on the output as well. Yeah, when we plot outcome-wise box plots, it gives more insights, right? If you give even give a glance for all these variables, you can see almost all the variables show different distribution for each output category for the patients who are having diabetes and non-diabetes patients. It's mostly the diabetes patients has higher variable values throughout these features. Even if we take simply age, for the diabetes patient, age distribution is bit higher. The mean value is bit higher than the diabetes patients, which also makes sense practically as well. As you grow older, as you become of age, there's a higher chance of getting diagnosed with diabetes. So like that, so this we can consider as a multivariate analysis as well. So these are like very basic graphical visualizations we can do, and there are many. You can go into the more deeper and deeper. Like you can select 2 features and go deep into those features to see whether there are relationships and all. Again, I'm highlighting that when doing this exploratory data analysis, having a thorough understanding about the problem you are solving and the domain, it will give you a lot of idea about what sort of analysis I should do. Like let's say now, if there's anyone who is coming from the medical background in this workshop, you might be getting a lot of ideas like to check the relationship between glucose and insulin, or the blood pressure and thickness, with can't those be having a relationship, and so on. So which sort of analysis you want to do is based on the problem you are solving and the background knowledge you are having. So apart from these type of graphical visualizations, as I mentioned, you can do some relationship checking with among the predictor variables. So here what we have done is checking each variable distribution variation across outcome variable. And next here I have put the code to check the relationship between 2 variables, glucose and insulin. Maybe at a glance you can't see, it doesn't show any strong relationship, right? It doesn't show a line or something. But one thing you have to keep in mind is this is a sample data set. Even though sometimes data set doesn't show, if you have the knowledge that these 2 variables should like have a relationship, then you can use any variation, different method of graphical visualization and try to find the relationship further. So here I'm not going with that, but of course you can try with yourself using different methods. But here also you can like see no diabetes patients more lying more in the lower number category in terms of insulin and glucose, which again makes sense when the glucose level is low. It's low. There's a low percentage of likelihood to get diabetes. So with this exploratory data analysis, now we have derived some of the conclusion that we have identified there are some missing values that we should handle. Some, even though they were not we couldn't see them at a glance, they were hidden with 0 numbers, but through the visualization, we could identify them with the domain knowledge as well. And we also identified some of the outliers, like in the pregnancies, which we can decide to treat through imputation or some technique. So the next step after the exploratory data analysis, understanding the data set and identifying patterns and data issues, it is the data cleaning. So under the data cleaning, before going to the data cleaning, is anyone having any question? No one? Not only questions, like if you have any ideas, like why can't we do this sort of analysis or something, you can like share it with us. Okay, cool. I'll go to the data cleaning part. Yeah, so first, under the data cleaning, first we'll be working on handling missing values. As I mentioned earlier, we have identified that these set of variables having a number of zeros, and in practical scenarios, it's not possible. Hence, we consider them as missing values. And so here first, what I have done is I have replaced these zeros with null values, which is not a compulsory step, but I have just done that. After that, I'm taking the null count for each variable, not only the count, also the percentage of null values. So here, if you see number of null values in the glucose variable is 5. So altogether, we had like 768 entries. Out of that, only 5 records having null values, which is very low. And of course, in this case, we can go with imputing these null values. It won't do a big harm. But you need to make sure that you are doing imputation with the proper meaningful value. And blood pressure also, we can say fairly low. But if you look into this skin thickness and insulin variables, those are having quite a large number of null values. Even like if we directly take the percentage of null value count, it's almost 30% and 50%. So if we take the insulin, it's a half of the records are having null values. So in this case, just think like we decide to impute this insulin variable, null values in the insulin variable with mean or median. So we'll ended up having more than half of the records having the same value. In that case, this variable might not do a big impact, give a good information for the model training purpose as well. So when we have like a large number of null values in a given variable, and let's say we have like quite a number of variables as well, we have like 20-30 variables also, then of course we can go ahead and decide to remove these variables as using them with the imputation might not add a value, given we have other variables with complete data available. But if you're having like a lesser number of variables, let's say you have only 4 and one is insulin, which is having this much, then you might come up with better ways of imputing this. So one of the basic methods of imputing null values are using the mean or median based on the distribution of that particular variable. But in addition to that, like slowly depending on that variable itself, we might consider getting help from other variables as well. So let's if we assume there's a relationship between glucose and insulin, and since the glucose doesn't have null values, it's only 5, we can get help from glucose variable to impute the insulin variable. If we can like identify a relationship between those two, to impute the null values in the insulin, we can use the glucose variable as well, without slowly depending on the measurements of insulin variable itself. So in those scenarios, like if we really want that variable, and if it has higher null value count, we can go with those sort of advanced mechanism which will add the actual value to the variable and eventually to the model training. So in this case, apart from like checking the null value count in each variable, I have done a quick analysis to check the number of null values for each patient as well. So here I have taken the number of patients who has more than 3 null values. That means patients who are having 4 and 5 null values. So here altogether we only have 8 variables. Out of 8 variables, 5 variables are having null value, means more than half of variables are having null values. And again, if we take the number of patient count like that, only 7. So in this case, we can decide to drop these patients and go ahead, because it's a lower number, and for those fewer number of patients, we are having only half a data available. So we can decide to drop it. So likewise, there's no straight answer of hard and fast rule. It's always given the scenario, given the external knowledge you can try out. And of course, in this case also, you can build 2 models, one having the insulin variable imputed, and another variable without the insulin variable, and you can pick whatever give best accuracy. So always try out different methods. There's no hard and fast rule when it's come to these sort of tech analysis approaches to handling missing values. So here, since it's only 7, I'm simply dropping those 7 patients. Priyanka, you have asked a question. If there are 50% of null values, do we need to remove all the rows which are having such null values? No. If you now you saw the count of patients is it's almost 50%. If we drop 50% of records, it's quite a lot. We are going to lose half of the data points. Rather than dropping all the patients entirely, you can consider dropping that column only. So it will do less harm. We will only lose information related to insulin only. But if you decided to drop all the patients, I mean the entire patient record that having null value for insulin, then we are going to lose a lot of data. So it's better to, if you want to drop, actually, which is in this case is better, you can consider to drop that particular variable only, not the entire patient record. Yes. So that's why I said, so with our the practical general knowledge, we know that insulin level and diabetes are closely related. And here we only have 8 number of features. In that case, that's what I said, if you see, I also didn't drop it. You can go ahead having that feature, and when you are training the model and trying the accuracy, you might decided to train the model with and without insulin and see which is giving the higher accuracy, and then decide to drop it or not. That is a best way in this scenario, because given that these two are highly correlated, I mean, it may, with the practical knowledge we are having, we know that there's a direct causation between diabetes and insulin. It's okay not to drop it, but if you don't have that sort of a strong, not you, but practically, if there's no that sort of a strong evidence that these two are having a strong relationship, then you can obviously drop it. So as I mentioned, if you have a lot of variables already, then you can drop it. But if you have lesser number of variables, and you know that there's a causation between those two more than a relationship, if you know, if the insulin level is very low, then it's difficult to absorb the glucose, and there's a higher chance of getting diabetes. So you know that there's a good relationship. So in that case, you can decide to keep going with that feature. And as I mentioned, test it 2 models, and based on that to keep it or not. I hope it's clear. Yeah. So here what I have done is I have dropped the 7 patients who had null values more than 4. And then after that, what I have done is I have done the imputation of this variable for the missing values. Here I have done a very basic level of imputation. For this, I have used, for almost all the variables, I have used the median. So if the distribution of the variable is quite normal and there are no outliers, and if the missing values are random, then of course you can go ahead and impute the missing values with mean. But as you saw in this box plot, most of the variables are not normal distribution. Those are skewed and having a lot of outliers, as well as the missing values are not random. All the missing values are from the bottom tail 0. So in that case, it's recommended to impute with the median. So this is the very basic method of imputing. So as a bit better way, you can decide to impute. If you take the glucose variable, you can impute the diabetes patient separately. That means for them, you can take the mean glucose value for diabetes patient and impute those. And for the non-diabetes patient, you can separately take the mean and impute them. Because it even in these plots, you show that it shows if we take the glucose for the non-diabetes, it's 105 likewise. For the diabetes patient, it's 130. But if you take the total distribution, its mean is median is 120. So there's a big difference, right? So imputing the diabetes patient and non-diabetes patient separately make more sense. It retrieve the information better than in a better way than just imputing the entire population at once using one value. So of course, here I have not done that. If you can try it by yourself and see if it causing any improvement in the accuracy as well. So after doing the imputation, we can obviously check the null count. Now there's no null value. Also, we can just plot the box plots and again see if our imputation has done any distortion for the distribution, and it seems like no, right? Still these distributions are same. It just that those 0 values has been cut off. With after this handling missing values, then we can go to the treating outliers. So in this box plot, I have identified 2 outliers. One is of course with the pregnancy variable, as I mentioned. It would be better if we treat them those upper boundary outliers as outliers, because they can cause for overfitting of the model, even though it's likely to have 17 or 15 pregnancies in practically. It's highly unlikely. And also, if we take the low blood pressure, we can see even after removing the 0 values, there are some more outliers between 40 and 20, which is again highly unlikely. If we take a live human, it's unlikely to have this sort of blood pressure. So we can treat those two variables to remove the outliers. So to keep the distribution and to avoid any distortion of that, I have, let me show it with the picture itself. For pregnancies, these outliers has been replaced with this max without outliers. And same for the blood pressure. I have replaced these outliers with the minimum value without outliers. So using this code snippet, I have replaced the outliers of those two variables. So here simply using these equations, I have calculated the max boundary without outliers and the minimum boundary without outliers for blood pressure. I hope you have covered these percentiles and interquartile range of this box plot in detail in previous sessions. Yeah, so after handling treating for the outliers, we can see we can't see them anymore, and it has not had a big impact on the distribution as well. It's still the same. So those are two of the common data cleaning that we do with any data set. So this data, since this data set has like a limited number of fields and all are numerical, we couldn't go with like many data cleaning parts. But let's say now here we had some floating numbers as well, right? So we might given the problem, we can like decided to like round off them. Like if we are having many decimal values, to round off to 2 decimal values. And also like if it's a text, if it's object variable, of course, with the with these all data are entered by humans, so there can be human errors. So of course you have to treat them like how to convert into a one format, maybe uppercase, lowercase, and you have to remove the extra spaces, and there can be spelling issues. So when the text data are there, you have to do those sort of cleanings as well. Anyone has any question? Do we need to remove the outliers? If we keep outliers as it is, it will be impacted to the final model. I'm asking considering all the variables. Yeah. So if you can see that we could see outliers in like almost all the variables, but we didn't remove all of them, right? So these outliers are statistical outliers. That means based on this sample data set, based on the statistics, these are mentioned as outliers. But as I mentioned, like for example, in this age, we don't need to treat these outliers, because in practical scenarios, there are patients who are above 65 years old. And to make this model more generalized, to have like a more generalized data set, it's better to keep them. You don't need to treat them. So, but here, again, here the pregnancies, I have treated them, but you might decide not to. Here I have treated them because those are extreme values. And since it's highly unlikely to have like 17 pregnancies, even though it's possible practically, it's highly unlikely. That's why I have treated them. So always you have to remember these plots comes as like based on the sample data set according to the statistical measurements. You have to always incorporate your domain knowledge and the problem, knowledge related to problem, and analyze and see, question and see, are these actually outliers or not? So in this case, the blood pressure, it can be outlier. Also, it can be like some incorrect data as well, because it's impractical to have at least as per my knowledge, I'm not coming from a medical background, but it's unlikely to have that sort of a low blood pressure, right? So you always have to question with the domain knowledge, can these be outliers? And yes, mostly if those outliers are practical, it's good to keep them to make the dataset more generalized. But again, as I mentioned earlier, with the missing value, drop in the missing value column, you can try multiple models, training a multiple model with and without outliers, and see the impact, because it depends. It's hard to say exactly it will increase the accuracy or drop the accuracy. It's better to always try. But one thing to keep in mind is always you need to question with the domain knowledge you're having, can these be actual outliers, and so on. I hope it's clear. Yeah, so these are some sort of basic data cleaning that I have performed for this data set, given we only have the numerical variables. So after that, as the final step, before going to the modeling, we'll be doing the feature engineering part. So in the under the feature engineering, we will, so here these skin thickness, insulin, BMI level, those are the measurements. Those are the raw data that we have collected. Of course, you can go ahead with this column as it is and use for the model, or else if you have more knowledge, you can like decide to create your own features. Like maybe you can create like BMI to skin thickness ratio, or maybe instead of directly using the pregnancy, you can have, as you have more pregnancies, you are more prone to the diabetes. So you might consider, instead of directly having pregnancies, to have the square of pregnancies as a variable, as it will do a big impact as the number goes higher. So likewise, you can like think of creating new features. So before going to that feature extraction part, here I'm performing a quick correlation check on the features. Yeah, so here as it becomes darker red, it means it has a strong positive relationship. So as you can see, it's barely barely a variable has a relationship with another one, correlation actually. So if you can see, age and pregnancies has a fairly strong positive relationship, which also makes sense. As you grow older, the number of pregnancies can go high. And also if you take the skin thickness and BMI, that also makes sense in the practical scenario. Apart from like checking the correlation between these variables, if we have a look into the correlation of these variables with the output, we can see there's no much, it doesn't show a good relationship. Apart from, besides this glucose variable, the rest are having like showing like lower correlations. So here again, just because it doesn't show a good correlation doesn't mean that these are not connected. And also the other way is the same. Just because two variables or a variable and outcome shows a good correlation, it doesn't mean that there's an actual causation, that the let's say here now we had some column like the job, and you see that job has a big correlation with the outcome, but some can, in real world scenario, some can argue that the job can't do impact on the outcome. So likewise, with our knowledge, we know that these all medical measurements can do impact on having diabetes or not. So even though these values show low, according to the sample dataset, with the domain knowledge we are having, we can go ahead with this dataset, as we know in medical domain to predict whether the patient is having diabetes or not. These measurements are heavily used and critical. So with that, coming to the feature extraction part. So as I said, here you can consider creating new features and modifying the existing features into different formats. Those things can be done. So here I have done one of the transformation, which is the bucketizing of some of the variables. So I have selected the BMI, pregnancy, and age variables, and I have bucketized them. That means I have mainly done with the intention of like reducing the overfitting and the improving the interpretability. Like, let's say someone is like, rather than telling like someone is with the BMI value 34 is more prone to diabetes, telling like someone who is overweight, having the obesity one, is more prone to having diabetes, makes sense. Like, it's more interpretable, right? And like sometimes there's no big meaning between like saying age 40 years and 41 years, 42 years. If you can say like teenagers, young adults, and old people, that would make more sense. So considering that, we can decide to like bind these some of the continuous variable into categorical variables. So here I have performed bucketizing on 3 of the variables. And also it's specifically easy, like if you have the domain threshold, domain specific thresholds to bind these data. For example, for BMI labels, like, you know, we have like domain specific thresholds. Like if the BMI value is between these 2 values, it's underweight. Likewise, you can use those specific knowledge as well when you are creating features. Yeah. After that, I have found these 2 variables which are highly skewed and has a quite larger number of outliers. So to reduce the impact of those outliers and to make it a bit normalized, I have applied the log transformation for the insulin and thickness variables. If you can remember, yeah, see the insulin and the skin thickness, those are like highly skewed and has a quite larger number of outliers. So to handle that, I have applied the log transformation. Sometimes you can apply these things in the model itself as well. With that, after feature extracting, so now here we had the numerical features in our original data sets, but here we have created some categorical variables. In most of our majority of the machine learning model, it's actually almost all of the machine learning models, they are taking the numerical values as the input. They can't interpret the categorical text variable in most machine learning models. So we need to do something called encoding. That means to encode the text values into numerical values. So there are mainly 2 methods that we can follow. One is one-hot encoding. The other one is label encoding. So in the one-hot encoding, what we are doing is, like, if we take this BMI category, for each category, we are creating a separate column. BMI category underweight, BMI category normal, likewise. In the label encoding, what's happening? Each of these categorical variable, we are assigning a numerical value. So how you can decide which encoding method to use is, Like, let's say your category, if your categorical data is like ordinal, they don't have like any relationship or like a numerical order. If we take an example, as I said, if it's a job, if you are a doctor, engineer, teacher, among those categorical variables, there's no order, numerical order. So in those scenarios, it's better to go with one-hot encoding. But in these three, it's mostly we can say there's a numerical order, right? Underweight, BMI of underweight is lower than the normal BMI category. And it's lower than the overweight BMI category. Likewise, we have a numerical order. So in this case, we can go with label encoding. So here, and one thing you need to keep in mind is it's important you label them in a proper order. So to make it more clear, I have done the manual labeling here. You can use like existing like functions from the libraries as well. So to make it more clear, like since you need to have the proper order when you are using the label encoding, I have done the manual label encoding. For here, underweight is 0, normal 1, overweight 2. Likewise, I have kept the order when doing the label encoding. Yeah. And finally, after doing all the cleaning, speech extraction, encoding, finally, we can perform something called scaling data. Now, if you see these measurements, these different medical measurements has been taken from different units. Some might vary between 0 to 1, where some might vary between 0 to 1,000. So to make sure all the variables are getting treated same way, we need to, it's better to keep all the variables in a similar numerical range. For that, we can do something called scaling data. There are different methods available like min-max scaling, standard scaling. So here I have performed standard scaling for this purpose. And then finally, when we display the data set, it looks like this. Sorry, outcome column has come in the middle. But if you disregard that, you can see since we have used this bind between a -1 and 1. Yeah, so that's the end of data processing part. If you have any questions, I'm happy to take them. Any questions? Like everyone is clear? Let me stop sharing the screen.
Thank you, Ms. Malshini. As we wrap up today's first session of the workshop, I would like to express our gratitude to Ms. Malshini Nissanka, data engineer at North Technology Group, for a valuable insight, and to all of you for your active participation. Now, as the time arrives for the last session for today's workshop, I would like to invite Ms. Ushani. The virtual floor is yours. Please enlighten us with your wisdom and expertise.
Hope you guys can hear me.
Yes, Ms. Ushani.
Okay, let me share my screen. Good evening all. So I hope you have enjoyed today's session so far. So I'll be picking up from where Malshini stopped the session. So now our data set is actually pre-processed and it is it is ready to feed into a machine learning model. So before diving into, so in my session, I'm going to showcase how to fitting a machine learning model and how to evaluate machine learning models. So before diving into fitting a machine learning model, I'd like to share some clues or the tips which will be helpful you to drive your machine learning projects into a success. So the first clue is when you are selecting a machine learning model, first determine the nature of your problem. So if it is a regression problem, so that means you are predicting a continuous value. Or is it a classification problem? Then where you have to determine the class for the which class that the given observation is falling into. So likewise, based on the problem that you are having, you have to select the machine learning model, and you can select set of machine learning models. So the second tip is always try to begin with the very simple machine learning models before jumping into a complex ones, because simple models are very fast to implement, and also it is very easy to interpret the results that which are given by the simple models. And also sometimes those simple models can provide you a very strong baselines to solve your machine learning problem. And the third tip is when you are trying a machine learning model, don't stick into one machine learning models. I'm recommending you to try out at least 3 machine learning models and compare the performance of these 3 models, and then you can select the best model to go ahead with. So I think these are some of the tips that I have learned when I'm dealing with machine learning related problems. So I think these guidelines and the tips will be helpful you when you are driving a machine learning model. So now let's start the today's session. So first, so I'm starting where as I mentioned, I'm starting where Malshini stop the session. So first we have to import the libraries. So here I have used pandas, numpy, matplotlib. So these are for the data manipulation and data visualization purposes. And here I'm using scikit-learn. So this scikit-learn library is a very important when it comes to the machine learning model fitting, because it provides you a set of tools which can be used for the data analysis as well as the machine learning modeling. And okay, so now we have import. So I ran this code snippet before, so I'm not going to run it again. So then, so here, this is to just in case if we need the original data set later on. So I'm making a copy of our original data set. So this is not a standard step that you should follow. So it is just in case I'm keeping a copy of my original data set. So then when it comes to the supervised machine learning problems, this is a standard practice to separate your data features and the target variable into 2 different variables. So here you can see that we are separating our feature set into X variable, and we are assigning our outcome variable or the target variable into a variable called Y. So now we have separated our feature set and the target variable. So then, okay. So then next we have to, now we have separated our data set into features and target variable. Then we have to split our data set into 2 parts. So one is for the one is for the training and other one is for the testing or the validation. So when we are dividing or when we are splitting our data set into two different parts or two different parts, so there should be a ratio. So the most common splitting ratio is either 80 to 20 or it can be 70 to 30. So that means the 80% of the data is relating for the training data and 20% for the testing purposes. So these ratios or the ratio of splitting your amount of data that you have in hand. So when we are trying data set splitting for the training and testing, so here you have to specify your feature set that we have created earlier, and here you have to specify the target variable. And in this parameter test size, we should specify the ratio for the test set. So in my case, so today I'm using 80 to 20% ratio split to split the training and testing sets. And then we have random state. So this parameter, actually we are using this to control the randomness of the data splitting. So in simple words, that means the anyone who is running this code, they are getting the same result or the same splitting what I am getting here, because we have set the random state here. So if you have specified the random state parameter, so that ensures that your results are reproducible at any time. The anyone who is running this code is getting the same split or the same result. So then now we have splitted our data set into two parts. Now we are doing feature scaling. So basically, feature scaling is very important because, for an example, think that in our data set we have features which are having very big numerical values. Sometimes there may be features with very small decimal numbers, or sometimes we may have category encoded categorical variables. So in this kind of scenario, so the feature values are in different scales. So we need to convert all the variables or the features into a same scale. So the importance of this feature scaling is when we scale our data, the model will give same importance to all the variables, and it will focus on the patterns and the relationships in the data rather than the scales of the features. So that is why we need feature scaling when it comes to the machine learning modeling. So here I'm using standard scaler, and I'm initializing the standard scaler here. Then I'm I'm doing scaling for both feature sets in training and testing data. Now we are going to move into the training machine learning model. So before that, if you have any questions, you guys can ask. So if not, we can move forward. Okay, hope that everything is clear up to now. So I'll be starting model fitting in here. So here, as I mentioned earlier, today also I'm using a very basic or very simple machine learning classification machine learning model called logistic regression. Even though the name of this model is having regression, so we can use logistic regression model in both regression and the classification problems. Okay. So here you know that the objective of today's data set is today's problem is to predict a given patient is actually having diabetics or not. So that means our problem is a classification problem. So we need to take a classification machine learning model. So I'm trying out a logistic regression model today. So first we need to create an instance of the logistic regression model. So that is what I have done here. And then we should train the train machine learning model using our training set. So here for that we are using .fit function, and here we are specifying the training data, X-train and the Y-train. So that is how we train our machine learning model. Okay, so after we have trained our machine learning model, then we need to make predictions on the test set. I think you can remember, first we splitted our data set into training and testing. So training set was used to train our model, and now we have our test set called Y-test, and here it is scaled. So we given as the name for the X-test scale. So we need to make predictions by using the trained model, and then we are assigning those predictions to y-pred variable in here. So now we have built our data, we have built our machine learning model, and then we made predictions on it. Then what we have to do is, then we need to evaluate the performance of our machine learning model. So I think up to now, all the things are clear to you. So if you have any questions, you can ask. So if not, otherwise, we can move forward. Okay. So hope everything is clear to you. So when it comes to the model evaluation, so there are several matrices that we can choose. So think that we are working with we are solving a classification machine learning model problem, so that there is set of evaluation matrices like accuracy, precision, recall, and F1 score. So likewise, when it comes to regression kind machine learning problem, so there is another set of evaluation matrices. And also think that you are working with time series modeling, so there are another set of evaluation matrices to evaluate the machine learning model. So based on the model that you are, based on the problem that you are going to solve, the set of matrices will be varying. So here I'm using these four different accuracy model evaluation matrix called accuracy, precision, recall, and F1 score. So I'll give a brief explanation to these variables. Accuracy gives overall correctness of the model. That means it shows the percentage of total predictions that were correctly predicted by the model. So that is the idea behind accuracy. But as I mentioned, even though that accuracy gives a quick overview of the model performance, it might not be a best measure when it comes to or if our data set is imbalance. Imbalance in the sense one class is more common than the other one, so that means our data set is not balanced. In that kind of a situation, accuracy is not a good measure to evaluate our model performance. And the second one is precision. So that precision actually indicates the proportion of patients who are diagnosed with diabetics by the model that are actually having diabetes. So that is the meaning of precision in this scenario. So high precision is also will be important when cost of false positive is really high. in this case, what is the false positive? In our case, false positive is false positive is the non-diabetic cases incorrectly labeled as diabetic. So if you have identified patients who are actually not having the diabetics and we have predicted them as having diabetics, so actually it is a cause, because it will lead to unnecessary stress or treatment on the patient. So sometimes if the cost of false positive is high, then we need to improve the precision, and we need to get high precision. And the third one is recall. So recall actually indicates the proportion of actual diabetic cases that the model correctly identified. So that is the meaning of recall when it comes to this, when it comes to our scenario. So when it comes to the medical diagnosis or medical context, high recall is really crucial, because if we are missing out true cases, so it can be dangerous. For an example, think that the patient who is having a disease, and the model is predicting that this patient is not having that particular disease. It can be diabetes or any other disease. So if we have predicted that this patient is not having any disease, so that patient is not getting any treatment, so it will worsen the condition, medical condition of that patient. So that means these kind of cases are really dangerous when it comes to the medical context. And the fourth one is F1 score. Basically, F1 score gives the harmonic mean of the precision and recall. So there may be some situations where we need to, at the same time, both the precision and recall are important. So in this kind of a scenario, we have to use F1 score for the model evaluation, or we need to focus on the F1 score rather than the other evaluation matrices. And so in this case, I think you may get a question. So now we have 4 evaluation matrices. So what are we going? What should we choose from them? So actually, choosing right evaluation matrix for a machine learning model, depending on the specific goals or the specific objects of the a project that you, or the problem that you are going to solve. Based on that, you can choose the evaluation matrix to evaluate your machine learning model. For an example, as I mentioned earlier, in medical context, if the predicting the patients who are actually having the disease, if it is crucial, then we should focus on the recall. So we should do all the things to improve the recall of the recall of our model. So likewise, based on the objective and the specific goals of our project or the machine learning problem, you have to select which evaluation matrix that we should focus on. So that is the theory behind selecting accuracy evaluation matrix for evaluating your model. And then here you can see, so here I got a print of the accuracies, precision, recall, and F1 score for all the for our model. So here you can see that our model has given 76% accuracy, and the precision is around 68%, and the recall is around 65%, and the F1 score around 67%. So that means our model is predicting, and it is somewhat good in performing. And here you can see we have another variable called confusion matrix. So this is the visualization of the this is the visualization of the confusion matrix. So I'll explain you how to interpret this confusion matrix. So this value, the 82, so it represents the count of currently identified non-diabetic cases. And here we have 36, and it represents the count of correctly identified diabetic cases. And here, these values represent the wrongly identified cases. So 19 represent the count of diabetic cases incorrectly labeled as non-diabetic, and these 70, value 17, it shows the count of non-diabetic cases incorrectly labeled as diabetic. So that is how we are interpreting a confusion matrix. So we can use confusion matrix also to see whether how the instances are, classified into 4 different classes. And here, so before we here we got the overall accuracy, overall precision and recall for the both classes. That means for the overall model. So sometimes we when it comes to the classification problems, we might needed to get the how we might needed to see how our model is working on each class. So for that, we need to use classification report. So it provides class-wise breakdown for how the model is working for the class-wise. So here you can see that all the precision, recall and F1 score values are higher for the non-diabetic class. So 0 represent the non-diabetic class and 1 represent the diabetic class. So here you can see all the precision, recall and F1 score values are higher for the non-diabetic class. So that means our model performs better on identifying the non-diabetic cases than the diabetic cases. So that is the meaning of this particular representation. So when but I mentioned you that in our case, our objective is to classify as much as possible number of instances or the patients who are having diabetics correctly. So that is our objective. So that we need to increase the recall of the class 1. So because it represents the number of patients who are actually having the diabetic. So in our case, we should focus on the recall and we should focus on this one, this 0.65 value as well. And so this is how we visualize the classification report and confusion matrix. And there is another measure called AUC. So get the AUC. AUC means the area under the curve. Under the curve. Curve is the receiver operating characteristic curve. So if you want to get the AUC curve, so you have to plot the AUC value. We have to plot the ROC curve and get the area under this curve. So here you can see that AUC is 82%. Before interpreting this value, I'll explain what AUC actually measures. So actually AUC measures the model's capability in differentiating between two classes. So here we have two classes. So this AUC measure gives the capability of the model in differentiating between two classes. So if our AUC value is closer to 1, so that means our model is highly capable of differentiating in between two classes. So here you can see that we have obtained 82% value for the AUC. So that means our model is highly capable of differentiating between non-diabetic class and the diabetic class. So that is the meaning of AUC value, and that is how we interpret the AUC value. So now we have trained our model and we evaluated our model. So if you have any questions, you can ask. You can unmute your mic and you can ask. It seems like there's no any questions, so we can move forward to the next part. So now I have showed you how to train a model and how to evaluate a model and how to interpret the different evaluation matrices. And then now we are going to check the class distribution. So when it comes to the classification problem, so more when it comes to real world scenarios, the most of the classification problems, the classes are not balanced. So that means the outcome variable, the distribution of the outcome variable is not balanced. For an example, if you think about employee turnover risk prediction model. So then the employees are, the most of the employees are belonging to the non-terminated class, and there are only few cases who are belonging to the terminated class. So likewise, where most of the time when it comes to the classification problems, our the outcome variable or the target variable is not distributed equally. So so we have to handle that problem. So in our case, here also you can see that somewhat class imbalance. So it is not as much as high, but it is but there is somewhat class imbalance. So here you can see that most of the instances are belonging to the non-diabetic class, and only 262, that means around 35% instances are belonging to the diabetic class. So that means there is a somewhat class imbalance. So I'll show you how to handle that imbalance problem. So there are different ways of handling the class imbalance problem, but here uh, I'm using a resampling technique to address the class imbalance problem. So in here, when it comes to the resampling, we can use oversampling or either undersampling to address the class imbalance problem. But here I'm using the combination of smarting. Smarting means the oversampling and the ENN, which means the nearest edited nearest neighbor. So I'm using the combination of these two techniques. So SMART is in the sense synthetic minority oversampling technique, and ENN is in the sense edited nearest neighbors. So when we are applying SMART, so it generates synthetic examples for the minority class, and the ENN, it is using for cleaning the data by removing any misclassified instances among the nearest neighbors. So basically, we are using a SMART technique to generate synthetic samples for the minority class. And we are using ENN to remove the noise generated by the oversampling. So that is the idea behind SMART and ENN. So today I'm using the combination of SMART and ENN to address the class imbalance problem. So here Here also we are separating again. We are separating our data set into features and target variable. Just to be clear, I'm again do the same steps, and also then what we are doing is then we are splitting our data set into two parts, and after that we are initializing the smart ENN instance. And also here also we are define the random state to make sure that our results are reproducible. And then after initializing the smart ENN function, then what we have to do is we have to apply the over resampling technique to our data set. So here I want to specially mention that, and you should remember this one. So we are applying smarting or resampling only for the training set. Because we need to keep the testing set as it is. That means we need to keep our testing set with the same with the actual class distribution. So we are applying smart ENN only for the training data. Then, so here we have applied a smart that resampling for the training data. So after that, we are again doing the scaling for the training set as well as the test set. And then we are initializing the logistic regression model. And then we are fitting logistic regression model on the training set, and we are training our model on the train set. And then we are making predictions on the test set. So that's so now we have trained our model, and we have made predictions on the test set as well. So here also I'm using the same evaluation matrices that I have used earlier. So here you can see that you have got accuracy. Here accuracy is 68 and precision is 53. And recall is 81 and F1 score is 64. So if we have go to the first model that we fitted. So here you can see the accuracy is 76. Now it is around 60. So that means there is a there is a significant decrease in the accuracy. And but here you can see that the recall is here at the first model we got around 65%. But in the second model, after handling the imbalance problem, so we got recall, and we have increased our recall value up to 81%. So that means our objective, we have obtained our objective, because I told you our objective is to increase the recall value. So because we need to identify the most patients now, as much as possible patients who are actually having the diabetes. So that is our objective. So we have achieved our objective when it comes to this case. And here also, this is a classification report for the second model. That means after handling the, or after addressing the class imbalance problem. And this is the first classification model we got before evaluating, before handling the class imbalance problem. So here you can see that in first model, all the variables, all the evaluation matrices are higher for the non-diabetic class. So in here, when it comes to this classification report, so you can see that we could be able to increase the recall of the class 1. So that means we have achieved our objective because we needed to increase the recall. So that means we need to increase the identified number of cases who are actually having diabetics. So, and also the recall is also in for the diabetic non-diabetic class is also 0.61, which is acceptable one. And also here, in confusion matrix. So now you can see that there is a slight decrease in the number of the count of the cases correctly identified as the non-diabetic cases. So there is a slight difference here, decrease in here. And when it comes to this one, so it shows the count of correctly identified diabetic cases. So here you can see that there is a slight increase in this value. So previously we got 36 and now it is 45. So there is a slight increase in the count of correctly identified diabetic cases, and now actually the correctly classifying instances are somewhat good. And when it comes to our objective also, we can see that we have achieved our objective. That means we have increased the value of the recall. And there also I have plot the ROC curve to get the AUC value. So here you can see we have obtained 83%. Even though there is a slight increase in the AUC value, we can say that we can interpret that our second model is also really good when interpreting the when predicting the diabetic class. And so then, all these things done, we have done all these things to improve the model performance. So there are other ways, other techniques that we can use to increase the accuracy or increase the performance of our model. So one is cross-validation, another one is hyperparameter tuning. So we are performing cross-validation and hyperparameter tuning also to increase the performance of our model, as well as when we are if we do cross-validation and hyperparameter tuning, so it will help to reduce the overfitting of our model, and it could help to generalize our model into the unseen data or the new data. So that is the idea behind cross-validation and the hyperparameter tuning. So there are several methods which combines hyperparameter tuning and the cross-validation. So today I'm only focusing on the grid search CV, which combines the cross-validation and the hyperparameter tuning. So when it comes to the grid search CV, we have to manually define the parameter grid. So here, these penalty, solver, and the max iteration, so all those are the parameters which are presenting in logistic regression. And here you have to, these are the logistic regression, the parameters in the logistic regression, and here we have to manually specify the values for each of these parameters. So that is the case in grid search. So we have to manually specify the parameter grid. So now we have defined our parameter grid. Then we have to initialize the grid search CV, and also we have to specify the folds for our cross-validation step. So here I have used 5-fold cross-validation. So if you need, you can increase or decrease the number of folds for the cross-validation. And also here I have used recall as the scoring method, because we are focusing to recall where increasing the improvements in the recall. So I'm using recall. So based on your object, you can either use recall, precision, or F1 score, accuracy. You can use any of the matrices based on your preference. And after initializing the grid search, then what we are doing is we are fitting grid search CV to our training data set. So this is what we got as the result for the grid search CV. So I think we can't interpret these results. So that grid search CV itself providing us these functions to get the best parameters. To get the best parameters from the grid search, we can use grid search.bestparams. And to get the best score obtained from the cross validation, it provides best score function. So here we have got the values, the best parameters for our logistic regression model based on the given training data. And this is the best cross validation score we have obtained for this training data set. So after that, now we have cross-validated, and then we have to retrieve the best model we have obtained from the grid search. So that we have to use grid search.best estimator, and we have to assigning it to the variable called best model, or any variable. You can use any variable here. So after retrieving the best model from the grid search, then we have to make predictions on the test data using the best model which we have retrieved from the grid search. So that is then after making prediction on the test set, so we are assigning this into this new variable called vibrate CV. And here also I'm using the same set of evaluation matrices. So here you can see earlier we got around 60% accuracy, but here now the accuracy is around 72%. So that means there is a significant improvement or the increase in the accuracy, and the precision is 58 and recall is 80. Previously it was around 81%, so now it is around 80. So we can neglect that decrease. And when it comes to the class-wise classification report, so here you can see that a small drop in the recall for the diabetic class, and there is a small increment in the recall value for the diabetic class. So that means these two values are actually acceptable in a classification problem. And also I have plotted the ROC curve to get the AUC value. So here you can see now the AUC value is 80. So that means previously we got 83%. Now it is 80, mean that there is a slight drop in the AUC value. So so I have created this model just to showcase you how to handle a machine learning model, how to fitting a machine learning model, and how to handle a class imbalance problem. So there are a lot of classification machine learning models that you can use to solve a classification problem. So actually that is the end of today's presentation, today's session. So if you guys have any questions, you can ask. If you don't have any questions, actually, I want to give a briefing of the summary of today's session. So we have started with, we have covered a lot of parts from the data pre-processing to understanding the basics of machine learning model, and then we described how evaluation matrices can be used when we are evaluating a performance of the model. And then I'll show you how to use how to handle the class imbalance problem as well. So those are the main topics that we have covered in today's session. I think that most of the you guys are coming from you are undergraduates. I hope that you will not stop your data science journey from here. So don't disturb from here. So always try to keep experimenting in different data sets and different solving different kind of different kind of problems, and always be open to learning things, because machine learning and data science is actually a very evolving fields. So the techniques, the tech stacks for the data science as well as the machine learning are evolving and changing day by day. So if you want to get into the industry, so you should be up to date by learning new technologies and the new concepts that are coming. So that is my final advice. And also remember, anyone can actually fit models, or anyone can do analysis, but the most important thing is storytelling from those data and interpreting your results to the non-technical stakeholders. So that is the main thing that you should have. So keep in mind, and I'm wishing you all best of luck in your new journey in data science and machine learning. I think they don't have any questions, Shamadip.
Thank you, Ms. Ushani. As we wrap up today's workshop, I would like to express our gratitude to Ms. Ushani Amarasekara, Executive Data Analysis at Mass Krida, for her valuable insights, and to all of you for your active participation. Before we end the meeting, I would like to request everyone to switch on your cameras to take a picture of today's session. Okay, thank you everyone. We hope you leave today's session with a deeper understanding of data science and machine learning. Thank you.